I want to derive the relationship between the focal point and the radius of curvature for a spherical mirror. And so the way that we're going to do this is we're going to consider a parallel ray coming in some height h above the optic axis, hitting a point x on the mirror. We know that it's going to reflect through the focus of the mirror, as like so. Okay. Next, I want to consider a radial line from the radius of curvature point C to the point X. Now remember that this will, by definition, be normal to the surface of the circle, or the reflector here. Maybe a tricky one. Oops, gotta go a little higher. And as such, by the law of reflection, it's going to bisect this angle here, right? So this would be the angle of incidence. I'm just going to draw that these are equal by the law of reflection. Okay, since these angles here and here are opposite interior angles, they are equal. And since this angle is also equal to this angle, that means that this side, FC, has the same length as FX. So I'll write that FX is equal to FC. Why is that? That's because the angle FXC is congruent to the angle FCX. Yeah. And therefore, FX is equal to FC. But notice that we could have chosen X to be any position. And so if we allow X to be P, so let X equal P, then what does that mean? That means that FC is equal to FP. And if we define this distance to be the focal length, that's a lowercase f, then what do we find? Well, that means that FC plus FP will be equal to F plus F, which is equal to 2F. But this distance, FC plus FP, is just the radius of curvature, R. And so we get that that is equal to 2F, which means, of course, that the focal length is equal to half of the radius of curvature. And that's that.